Okay, guys, sorry, I got cut off there. So on to part C from the test review open-ended. Number 2, to find the total rotational kinetic energy and translational kinetic energy together, right? We know that must be equal to the gravitational potential energy that the object has on top of the slope, whether that's a hollow or a solid sphere. So the total kinetic energy, the sum of the rotational and the translational kinetic energy must be equal to mg. But we know that the rotational and kinetic values are going to be slightly different depending on the shape of the object. So question part D asks us to kind of elaborate on that. So technically we know that the hollow sphere is going to have greater rotational kinetic energy than the solid sphere, which means that the solid sphere would win the race. The solid sphere would have more translational kinetic energy. Okay, and then there's more drastic explanations there under part D. The translational kinetic energy will be greater and the rotational kinetic energy will be less for the solid sphere, as it will require less energy to rotate it about its center because mass is uniformly distributed. The opposite is true for the hollow sphere. The translational kinetic energy will be less and the rotational kinetic energy will be greater for the hollow sphere, as it requires more energy to rotate the object about its center because the mass is located further away from the axis of rotation, further away from the center. Okay, and there's also a multiple choice question that was similar to that in one of the Google forms from last week. I suggest that you again take a look at those. Okay, on to the rotational dynamics multiple choice question. So for number 7, when it asks for linear momentum, you must look at the velocity. Okay, the velocity is technically the velocity of the center of mass of the disk. Okay, so when we're talking about translation, it's the center of mass in which we use as a reference point for movement. So velocity at the center of mass will be equal to omega times the radius. So we plug that in for V sub cm. So the linear momentum will be mass times omega times the radius. We're substituting in V for omega times r. Okay, number 11 is one of the examples of a tricky type question. We know how to find the angular momentum. So if we know it's a point particle, we can plug in mr squared. We know omega is v over r, so one of the r's will cancel. Because the question asks for the momentum in terms of r or with respect to r, technically with respect to r, the momentum is m times v. Okay, so the answer choice is actually E because of the wording with respect to R. Again, I wouldn't ask you something like that on your test. I don't know if they'd ask you something like that on the AP exam. That the wording there is just tricky. So with respect to R means kind of like in addition to R, what would the momentum be? And that's M times V. Okay, number 23 is tricky only because you have to read it carefully. So in 23, the incline has no friction. If the incline has no friction, the object doesn't rotate, right? The frictional force at a radius is what causes the torque. If there is no frictional force, there's no torque. So there's only translational motion. So the entire potential energy must be equal to the entire translational kinetic energy at the bottom. And you solve for Z, you get the answer choice D, square root of 2gh. In 25, the wording rolls without slipping means that there is friction. If there's friction, the object rotates. So in 25, it will rotate. If it rotates, you must use the rotational equivalent of torque and Newton's first or second law, F equals ma, to find an expression for A, which is actually the same as one of the open-ended questions that was on your test review. Okay, same exact process, we get the same exact answer actually. So we use torque equals R times alpha. Force of friction at a radius causes the rotation. We plug that in for torque. We plug in our value for I, which is given to us, 2/5 mr squared. We plug in linear acceleration over radius for alpha. All of our r's will cancel. We have an expression for A in terms of force of friction. So we use Newton's second law to find an expression for force of friction. And then we plug in. So we substitute in for F of F. All the masses cancel. And we determine that A is 5/7 g times the sine of theta, which is answer choice B. Okay. Rotational motion free response. So again, number 2 is a little bit more complex than anything you'll see on the AP exam or the test that we take tomorrow in class. So number 3, someone asked me about part F. So part F is kind of tricky and a little bit more complex than what we would talk about, but we will talk about that, okay, because it's doable and you should be able to handle it. Although I wouldn't ask you a question with this many parts on your test. So in 3, you basically have a bucket tied to a string across a pulley. The axis or the axle of the pulley is tied to the roof. And in part A, we're asked to draw the forces acting. So on the actual bucket, we know that force of gravity and the tension will act at the center of mass. So you must draw those forces acting on the center of mass. For the pulley, the tension due to the support, so that should be a T sub S, and force of gravity act on the axle, which is the center of mass of the disc. And then there's a tension force that acts at a radius r from the center of mass on the disc that causes the rotation. Okay, so the location of where you draw those is very important. The tension of the support and the force of gravity act on the center of mass. The force of gravity always acts on the center of mass of the object. In part B, we need an expression for A in terms of constants. So we have to use the rotational equivalent of Newton's second law and the translational or linear equivalent of Newton's second law. There's only one tension here. Okay. So we plug in for I and for alpha. As per usual, our R's cancel. We have an expression for in terms of tension. We use Newton's second law to find an expression for tension, and then we plug in using the system of equations to find an expression for A. In part C, we're asked to find the angular acceleration, which we know is just the linear acceleration divided by r. We rearrange that a little bit to get the expression seen next to part C. Okay, so for part D, we need an expression for the magnitude of the tension in terms of those given variables. So we take the equation that we have for tension under part B. Tension equals 1/2 m times A. We plug in for A. Okay. We solve this equation over here for A, and then we plug in for A. And then we simplify, we get the t values on the same side of the equation, and we find that the magnitude of the tension is big M times little m times G divided by 2 times the quantity little m plus 1/2 big M, the magnitude of the tension. Okay, in part E, we're asked to find the velocity after the bucket falls a distance h. So the acceleration, the linear acceleration should be constant. It starts at initial velocity 0 and delta x is h. So you use the big 4 to find an expression for v. Okay, and part F is a little bit tricky. So it asks us to find the force on the pulley provided by the axle. Okay, which because of Newton's third law, we know that the force on the axle by the pulley is equivalent to that. So we're going to use that lens instead to solve because it's a little bit easier. Okay, so we take a look at the forces that are acting on the actual pulley, and we solve for the support tension. Okay, so because the force on the pulley by the axle is equivalent to the force on the axle by the pulley, we can use either set of equations to find the force of the support. We have the tension due to the support, which is positive, minus the force of gravity, minus the tension applied by the bucket is equal to 0. When we solve for the force due to the support, we find that's equal to the force of gravity times tension. We have an expression for tension from part D in terms of the given variables. So we need to substitute in for that T from part D. And then when we simplify, we can factor out a big M times G from the numerator. We get that expression here, which relates the tension due to on the axle or the tension due to the support to our other variables. Okay, and our axle has no linear acceleration, so we can set the sum of the forces in the y equal to 0. So the axle itself will not accelerate. Okay, only the bucket is accelerating towards the ground. The tension due to support is constant. Okay, and does not cause acceleration. It is tied to the axle, which is then tied to the ceiling. Okay, so those are all the questions asked via the Google form. Hopefully that helps. I will attach an image of the list of equations that you should have on your note card for the test tomorrow. Okay, tomorrow you'll head to classroom again, join the Google Hangout. You'll need your note card and your calculator. You'll attach your free response answers to the assignment in classroom.